So the next speaker is Mareldi Ahumada. She will present a paper M-K interdiction modeling for natural gas networks. So absolutely linking perfectly. So a couple of words about Mareldi. She's currently a PhD student at the University of Washington, Seattle, in electrical computer engineering. Her research interests are in power system resilience and multi-energy systems. Great topics. Prior to graduate studies, she worked in the power industry sector, focused on power generation, turbine design, and operation. Mareldi, the floor is yours. It would be great if you could stay within the 15 minutes. Thank you.
Yeah, can you hear me okay?
Yep, perfect.
Perfect. Thank you so much for the introduction. Happy to be presenting in this session. I am Mareldi, and I'm a PhD student at the University of Washington. And this research was done at Los Alamos National Lab with my mentors, Kaarthik, Russell, and Anatoly. We will be talking about NK interdiction modeling for natural gas networks and its impact on the power systems. And so briefly, just this presentation, we will go through the motivation that has been nicely presented throughout this whole conference and in the earlier presentations. The gas model we used, the problem formulation, and some case studies that we simulated. And as I mentioned, there's been a significant increase in the number of natural gas-fired electric generators, and the reliance of the power system on natural gas has been increasing. And so the unforeseen component damages, either cyber attacks from the presentation previous to ours, or natural disasters or disruptions in the gas network, can lead to at least loss of capacity in the power systems and outages in its worst case. And so this research, we wanted to focus its impact on the reliability side of things. As we know, most systems are N1 secure and can be operated in a stable state, even if there is one contingency or one damaged component. As we move from 1 to K or more interdictions, we incur in load shedding in order to return to a stable state. And so what we wanted to know is to find that impact and quantify it as K increases, and what are the worst case scenarios that we can run into. And so our approach in this research was starting off with a natural gas flow model. To the right, we can see our gas network with compressors and links, a consumer nodes that lead into the gas and into the power generators, and some injections. And so on top of this layer, if there is an interdiction, say some components get damaged, and we want to return into a stable state, we ran an algorithm which can give you the minimal gas shedding so that you can return to stability. And this is for some randomized K components that can be damaged, but which K components lead to the highest load. And that is what our K analysis focuses on, is finding that worst case scenario. And finally, the loss of generation capacity, as these consumer nodes in the gas sector trickle into the generators in the power sector. And so I'll briefly go into our gas modeling. mentioned before also was it's a directed graph with vertices and edges, and our components modeled in this particular study were pipes and compressors. You can find this gas models within the Los Alamos lab ANSI group at GitHub repository. And we focused on a steady state flow across a pipeline with the nodal pressure difference and the mass flow rates. This formulation is nonlinear, and so as I continue with the presentation, we'll see our approach on relaxations to solve for optimality. And we came up with a bi-level formulation of a max-min problem where we started off with solving for this minimal gas shedding algorithm as the inner problem or the defenders. So given a certain configuration where we know that certain components will be damaged and unavailable to operate, we want to find the minimum amount of unserved gas at the consumer nodes. And in the outer problem, the attacker wants to choose that configuration and specifically which components make the network most vulnerable and maximize the unserved gas. And for our algorithm, this is an iteration process where we solve for starting starting off with some initialization of a random attack. We solve for the minimal gas shedding, and then that solution feeds back into the outer attack as a constraint. And in the next couple of slides, I'm going to talk about how these min-max optimization problems work. So starting off with the minimum gas shedding, we want to quantify the unserved gas as a function of the summation of the gas delivered at consumer nodes and some unserved gas factor. This minimization problem is subject to steady state equations, pressure and flow rate limits, and mass flow balance in the system. And since we are talking about a nonlinear problem, it is hard to solve to optimality. And so we reformulated this problem as with a mixed integer second order cone relaxation, and that is used to reach global optimal of the solution. And this can be solved with off-shelf commercial and open source solvers and reach optimality. Going into the unserved gas and the maximization problem, that is to find a scenario with K components that produce the max unserved gas. And a trivial solution to this solution is to evaluate all NK combinations possibly. But as we know, that is computationally intensive and intractable for larger systems. And so our solution proposed is integrating this cutting plane algorithm by adding constraints, piecewise linear functions, each iteration that we solve till its convergence to E-optimal solution, we set the gap of convergence to 0.01%. And so basically the intuition behind this cutting, this linear function is that we upper bound our solution space with the remaining gas in the system per component as the amount of load left in the system available to interdict. Part of the art of this algorithm is finding cut coefficients that tighten the space and the upper bound as fast as possible to minimize the iterations that are incurred to find the solution. And so I'll briefly go through the results that we tested this algorithm on. We tested it in 3 test cases: the Belgian gas network with 42 components, New England gas network with 192 components, and finally, for scalability purposes, we tested it on a larger GasLib 582 network. As you can see on the plot to the right, even with small values of components being interdicted, the unserved gas at the consumer loads is close to half of the capacity of the system compared to its baseline operation. And so this really lets us understand the vulnerability of having coordinated attacks or coordinated disruptions in the gas network in terms of loss of capacity to serve load. And to the left, you can see a diagram of the Belgian network, and we can track to the specific components that lead to this worst case scenario as we interdict more and more components simultaneously. Going beyond 4 or 5 components being damaged simultaneously might not make sense in practice, but we wanted to interdict up to 95% loss of capacity, just to show the computational limits and understand theoretically what is going on. And in terms of performance, you can see that with few iterations compared to the analytical solution for millions of iterations and plus 9 days of computation time, this algorithm really is efficient and effective in computing and converging. And so even within a couple, half a second, we can find the solution for the Belgian gas network. And as each network increases in its size, it is still a feasible tool to get an intuition of the vulnerabilities. You can see shifts in time not depending on iteration, and that is because the inner problem, or the minimal gas shedding, increases its solving time with the increased components of each network, but the number of iterations tells you about the computing time of the outer or the attacker's problem. And now the link to the power system. As the loss of generation capacity, it's modeled by a quadratic equation where we have the power profiles in megawatts as a function of the gas withdrawal nodes, or the consumer nodes on the gas side. And similarly to the results of the gas side, we have a strong dependency where even with few components in the gas network being interdicted, you have a considerable loss of generation capacity. And this really can impact for some generating units that might be on demand and trying to be flexible for generation, power generation. Our 2 case studies I forgot to mention are the Belgian network coupled with the IEEE 14 bus system, and the New England network that was coupled with the IEEE 36 bus system. And to finalize some of the conclusions, to the best of our knowledge, this is the first systematic algorithm to compute this worst case NK analysis on the natural gas pipeline, and it has been computational effective and scalable. And for future work, we want to do a joint power NK interdiction analysis that not only has the ability to damage components in the gas network, but also jointly have some damages in the power sector. And also incorporating a more elaborate transient gas flow model instead of a steady state analysis for the gas side. Thank you for your attention, and I will take some questions.
Thank you very much for a very interesting presentation. We have a couple of questions from Dan. Thanks, Dan, for asking his questions. The first one is about the minimization of the gas load shedding, effectively. So can you focus, instead of gas load shedding, onto electric load shedding? And how would you do that, and what kind of challenges would you have into sort of shifting the focus towards electricity load shedding?
If I understand correctly, that is what I mentioned sort of in the future work, where you can not only as a loss of capacity in the impact in the power side, but also run an minimum power head for better intuition of the impact.
Yep. Okay. No, that is fair. Second question comes again from Dan about the modeling. And is there any chance, or do you see possible in the future to move towards a dynamic gas analysis, including line pack and all that, rather than steady state formulation? And if you could comment about potential tractability of that problem.
Sure. I think this also leads to into the future work. As I mentioned, this is a first approach to see a good starting point to understand the theoretical and computational limits of this model, but it's a good first step into transitioning into a dynamic state formulation. As of now, it is tractable, and with the incurrence of dynamics and transients, it could be a challenge for computing to global optimality and fitting into the cutting plane algorithm.
Yeah, no, understandably. I don't know if there are any other questions. Let me check. Not a moment, but feel free to ask more, of course. I got a question about the sort of potential utilization of this tool and algorithms. I mean, what kind of applications do you see? So you perform the analysis, and then how do we take the results and we make use of the results, for example?
Sure. I think this type of solutions and results can lead to a knowledge of the vulnerabilities in our systems and where they are located, and looking into planning or mitigating outages or disruptions in either network. This tool can really show us what the worst case scenarios are and plan on from there.
Okay, thank you. Is there any other question? Doesn't seem so, unless I can see any. Then I would like to thank you again, Mareldi, for very nice work. And yeah, we look forward to the next steps. It's pretty exciting, and particularly if you could develop this into sort of dynamic gas mode, that would be fantastic. But very well done, and very nice presentation. Thank you.
Thank you.